In this video, we're going to look at some other types of groups and algebraic structures we can use to draw Pascalois triangles. So far, we mainly looked at the Z mod N groups. Probably the next easiest one to look at would be Zn cross Zm groups. Okay, right here. So selected that under the group tab. These are ordered pairs of group elements. So the first component of the ordered pair is going to contain Z mod N elements. The second order is going to contain Z mod M elements. And the operation is just component-wise addition, where we keep the modulus in mind in each component. We'll go ahead and start with Z2 cross Z2, which is the default. All right, I'll adjust the number of rows right here to that. Now, to draw the triangle, since the elements are ordered pairs, we're going to have to change the seed. So I'm going to click on the seed tab, and I'm going to replace the 1 here, which is really the default for Z mod N. And let's put an ordered pair from Z2 cross Z2 in that position. And now we'll go ahead and draw the image. Okay, and we get something that looks like this. Now you'll notice we didn't get all 4 group elements. There's 4 ordered pairs in Z2 cross Z2. We certainly did not get all of them. And that's because just using 0, 1 is not enough to create or generate the entire group. So what I'm going to do is I'm going to go up here and change the seed. And let's put in a second value. And what I'll do will be, let's try 1, 0 in the second component. And what this is going to do is it's going to put 0, 1 down the left side, 1, 0 down the right, and then it's going to generate the interior just using the group operation, mimicking Pascal's rule. And you see we did, in fact, get all 4 group elements in this case. Let's change the modulus, the second component, and look at Z2 cross Z3. This will have 6 elements, 6 ordered pairs. And I'll go ahead and use the same seed I did before. And we get a more complicated structure in this case. But once again, we do generate all 6 group elements. All right, one thing that's interesting about this example, let me go back and I'm going to go back to a single seed. And let's say I put 1, 1 down both sides of this triangle. Generate that way. Notice I still do get all 6 colors. For Z2 cross Z2, I could have tried any combination of a single element down the side, and I never would have gotten all 4 group elements. But for Z2 cross Z3, if you put 1, 1 down both sides, you actually can get all 6 elements. So that's one of the things you can explore. That's more of an algebraic question as to why one element will generate all the group elements for Z2 cross Z3, but for Z2 cross Z2, one element won't cut it. As our next example, let's consider the group under the table here that we call D mod N, okay, which you can choose right here. This is known as a dihedral group. These correspond to symmetries of regular n-sided polygons. So this one we want to start at 3 or higher. If I do n equals 3, we'll have the symmetry group of an equilateral triangle. If I do n equals 4, that's the symmetry group of a square. N equals 5, a regular pentagon, and so on. Interesting thing about the dihedral groups is these are non-commutative groups. We call non-abelian groups. The operation is actually function composition, since the elements are symmetries, which are really mappings, and in general, function composition is a highly non-commutative operation. So this gives us a non-commutative group structure. So what I'm going to do here is we'll click on the 1D automaton again, all right? And let's jump to the seed. Now, we're no longer doing ordered pairs. So the default in the software for the dihedral groups is we're going to call the rotations, because polygons have rotational symmetries, or 0 will be a 0-degree rotation, or 1 will be a rotation of minimal degree. So for example, in the square, 90 degrees is the smallest non-zero rotation, so R1 would be 90 degrees. Let me go ahead and do that. And I'm going to put R1 right there. So that, since we're in D4, that's going to be a 90-degree rotation. And I do the image. It turns out there's 8 symmetries of the square, 4 rotations and 4 reflections. And if you notice over here on the right, we're not actually getting any of the reflections. We're only getting the rotations. I can change the seed. Let's say I want to do one of the reflections. They'll be numbered F1, F2, F3, and F4 in this case. Let's just do F1. And again, I'm actually not getting all 8 elements back, all 8 symmetries of the square. I'm actually just getting 2, and that's because a reflection undoes itself. Once you do it once and then a second time, it brings you back to just the equivalent of not doing anything, or the 0-degree rotation, which is why we're really seeing a mod 2 structure right here. If I want to see something more interesting, what I'm going to have to do, like I did with the Zn cross Zm, at least in some cases, is bump up the seed. So how about we do a reflection down the left side and a rotation down the right. And in this case, notice we do get all 8 elements. You got your 4 rotations right here, including the 0-degree rotation. You got your 4 reflections there. Oh, excuse me, these are actually numbered F0 through F3, not F1 through F4, but you do get all 4 of them right there. We can change the number of rows. So maybe let's say I want to go up to 128 rows. I'll enter 127 since we start at row 0. Okay, and we get a pretty interesting structure there. Start to look self-similar like many of these other pictures we've seen before. Let me do that one more time. Maybe I'll jump up to 512 rows. What you have there, and yeah, so clearly this nice self-similar structure is emerging, even though we're using this kind of interesting non-commutative group of order 8 that has corresponds to geometric symmetries of a square. Now you may wonder what happens when we change the number of sides of our insided regular polygon. We can do that. I'm going to scale back the number of rows as well for a minute here. So maybe I'll jump back here to 128. Okay, so we're still on, this is still D4, the symmetry group of the square. But now let's jump up to D5 and look at the symmetry group of a regular polygon. I'm going to keep the same seed with a rotation and a reflection. We don't need to change that. And if you look at this image, this is much different. This is a more messy image, and you may wonder, well, what's causing this difference between using the symmetries of a square versus the symmetries of a regular 5-sided polygon? But clearly, something different is happening. I'm basically putting the same 2 things down the sides, minimal rotation on one side, a reflection on the other. Let's change the number of sides again. So how about we go up to 6 sides? So this will be the symmetry group of a regular hexagon. There'll be 12 symmetries right here. 6 rotations, 6 reflections. And let's look at the image. And a little bit better than we saw with the n equals 5 case, but still not as nice as we saw with the n equals 4 case. So something is definitely going on here. There's some algebraic reasons behind that. I won't spoil them at this point. I'll let you investigate that. But the algebraic structure of these groups is very much connected with these images you're seeing. Let me do one more. Let's jump to D8. So this is the symmetry group of a regular 8-sided an octagon. And that's much nicer once again. So that's one of the interesting things you can explore with this software is you try different groups, try different things down the sides, when you get nice images, when you get messy images. And if you do this, you'll see it's really always going to connect back with the algebraic structure. So in this video, we saw a couple new classes of groups. We saw the Z2 or Zn cross Zm groups, and we also saw the dihedral groups, or the symmetry groups of the regular insided polygons. In the next video, we'll look at a few more new types of algebraic structures that will also allow us to construct some very interesting Pascalois triangles.